Good afternoon everyone, my name is Stephen Westman and on behalf of Team Umber I will be narrating our Milestone video presentation. Our group Umber is made up of the following members: Hunter O'May, Zoe Herbert, Tom Lund, Joseph Barker, Nick Farmer, and myself, Stephen Westman. We were given the task of designing a deployable bridge that can be used in emergency situations. Over the past several weeks, we have worked together to develop a bridge that we firmly believe meets the standards required from this project. In this presentation, we will be discussing our design choice, the materials used, the building process involved, preliminary testing, and our numerical analysis as of week 9 of the semester. Finally, we will conclude with what is left to be done for our project. The initial bridge concept was chosen from 6 proposed designs. These included 3 truss systems, a beam-based bridge, a triangular truss, and a simplified arch bridge. Here is a matrix of design options which summarizes the decision-making process in a quantified sense. As shown, each design was assigned a number between 1 and 5, 5 being the highest in 4 criteria. These criteria were deemed to be the fundamental aims of the design at this stage of the engineering process. They are portability, P, load capacity, LC, economic feasibility, EF, and weight, W. These are arranged first to last in terms of priority, whilst all unnecessary weights of 35%, 30%, 25%, and 10% were assigned in that same order. Using this weighting and the scores given previously, a final figure was assigned to each as shown in this adjusted matrix. Naturally, this is a flawed evaluation process, being based on estimated figures and roughly weighted criteria. Thus, the designs were also considered qualitatively, both in terms of the potential of each design and the progress which preliminary investigation showed. The simplified arch bridge proposal, which is favored in the matrix, also came with the prototype shown. Therefore, if chosen, the engineering process to follow would be one of refining an idea proven to work in general. At the prototype stage, the specifications of this bridge were approximately weight, dead load 9 kilograms, cost $90, volume 400 millimeters by 300 millimeters by 150 millimeters, and a load capacity greater than 150 kilograms. The prototype also showed potential in embedding sustainability in design, being adaptable, reusable, lightweight, simplistic in design, and made from minimal materials with low embodied energies. Not only did the given specifications generally exceed those predicted for other bridge options and the specifications set in the design brief, they were shown definitively through physical testing and building. Subsequently, we chose the simplified arch as our design concept. To finalize our specific design, we looked critically at this prototype, looking to improve for the final project on demo day. Firstly, our final design could not have gaps in the deck. Also, it had been shown to fail at the joins, so these were strengthened. The slope was generally agreed to be too steep, at a maximum angle of 45 degrees, which is where the ends of the bridge meet the horizontal. The overall height would be, particularly on a larger scale, excessive, though an overly shallow bridge would undermine the design concept and offer little strength. The angle 30 degrees was chosen as a reasonable angle for this maximum slope, which reduced the height to 260 millimeters as shown in the diagram. This is less than half of that of the prototype. The lower slope also decreased the amount of materials required to span the 1600 millimeter clearing, thus the bridge was adjusted accordingly. It is important to note that in choosing a slope design, we are considering the users of the bridge who are stated in the project brief as medical personnel, engineers, power supply workers, and other emergency services. The bridge is not for general use, and it is a temporary measure for emergency services. It is a reasonable assumption that these people will be able-bodied adults, particularly since they are being sent into a hazardous flood-affected area. As it can be seen, the plates that make up the design are not large enough to be the loading deck. Subsequently, this will be added as a separate part for testing purposes as shown in this sketch. This is not yet completed. Moving on to materials, research into materials was initially carried out by Tom Lund as seen in the table presented. Nick Farmer lent his expertise in deciding the materials, having a lot of experience with building materials and the like. His chosen materials for the proposed bridge design and current prototype are presented in the on-screen table. The built bridge is made from plywood held between steel L-beams and with steel bolts, nuts, bars, and brackets as detailed in the table. The first prototype had an approximate cost of $90 and a weight of approximately 9 kilograms. The current prototype has a weight of 11.53 kilograms, a 23% increase from the first prototype, and a cost of $76.75, a 14.8% decrease from the first prototype. The added weight in the current prototype isn't something that can be perceived as a significant problem. What is important is that the cost of production was reduced. In this segment, the building process from purchasing the materials to producing the bridge design will be outlined. Construction was done privately, taking approximately 6 hours to produce the current bridge prototype. Based on the current prototype, Nick Farm produced a construction plan detailing each step taken to produce the bridge design. On top of the initial tests of our first prototype, an investigation was carried out on the optimum angles for the simple arch bridge design. Tom Lund performed the investigation. He devised an experiment involving a very small-scale version of our bridge design. Referring to the photos, kitchen sinkers were placed on the loading deck of the model. His experiment hypothesized that the maximum load will be delivered when the angles being modified are set to 165 degrees. The results of the experiment were graphed and the optimum angle was found to be approximately 165 degrees. Although the experiment was not 100% accurate, it provided a reasonable indication as to what the optimum angle for the bridge would be. These results prompted the change to the simple arch bridge design, which currently uses the 165-degree angles. The numerical analysis for our bridge design was done by Hunter O'May. Initially, the method of joints was applied. The method of joints relates to determining the forces in a truss structure. The method of joints is relevant to our bridge as it has truss-like features with the bracing. However, these were simply preliminary calculations. Hunter took the analysis to the next level by modeling the bridge design in SpaceGas, a 3D analysis and design program for structural engineers. SpaceGas provides information on the deflection of the bridge and various other pieces of information. However, there is a limitation with this analysis. The properties of the materials used when producing information on the model were not considered. The bridge model has been adjusted accordingly in SpaceGas in line with the developments made with each prototype. Future work, aside from documenting the project, will include the addition of a separate loading deck, further testing on the final structure, and finalizing method for deployment on demo day by practicing with the actual structure and the entire team. Some small adjustments may also be made. This concludes our Milestone presentation. I would like to thank you all for listening today.